Yes, Khalid, what were you
The
saying?
latest one, the velocity and that one.
No, after drift
I
velocity
don't remember.
for the previous class,
No, I didn't
resistance,
get.
not
No, I didn't
resistance.
get.
You didn't get it. And Salman and Samaira?
Neither me.
And Samaira? Resistance and resistivity, that assignment. Drift velocity, so I have
No,
discussed
like
it
it
in the
comes by the end of the week. So
Okay, both the assignments
yeah, it
of
comes
both
together by the end.
by the end. So did you receive it for the past week?
Yeah, past week, yeah, I've had
Past
even
week
yeah.
you all are receiving.
Ma'am, I didn't receive the previous assignment.
Previous assignment you didn't receive, Samaira. Okay. All right. Okay, let's start the class then. Temperature dependence on resistance and resistivity. So see, in this we'll be dealing resistance and resistivity together only. The reason for dealing resistance and resistivity together is that resistance formula was what? Somebody quickly recall. What was the formula? Khalid, you only help us. What was the formula of resistance? Yes, Khalid? Look into the notes if you're not able to remember. Yes?
Rho is equal to m by ne square tau. Oh,
ML,
that's resistivity. Sorry.
ML, ML.
That's rho L by A.
Rho L by A, that is correct. ML divided by NE square A tau, which you were saying initially. This I was asking. Good, Khalid. This is of resistance. Shravya, you tell us for resistivity, formula of resistivity.
M by NE square tau.
Good. Only L and A gets eliminated. This becomes M divided by NE square A. Not A. Instead of A, you have tau. And E square A, just eliminate L and A. NE square tau. Now, regarding wires and the conductors that you have, for temperature range, that we'll be dealing here. So there's not a significant difference in resistance and resistivity. Basically, there's not a significant change in length and area. So if length and area does not change, length and area does not change, length and area, both of them do not change, then resistance and resistivity's difference doesn't change. Means what's making resistance different from resistivity? It's the length and area only. If length and area gets eliminated, then that becomes resistivity. So it's ultimately length and area. So length and area, if I say they are constant, so resistivity and resistance will also be constant. So basically what happens, your temperature range for the temperature range involved for the temperature range involved, there is no significant change in now there is no significant change in what? Your length and your area of cross section and the length. See, if I say resistance and resistivity, both of these are like terms, both of these are same terms, then why am I constantly referring resistance different, resistivity difference? Because of length and area only. Exactly. So if I say by any means your length and area will be the same, then it means resistance and resistivity will be same. So that's why whatever will be the change in change or variation of temperature on resistance, we'll be taking it as same on resistivity, because for the temperature range involved, there is no significant change in length and area. Length and area. That's why resistance and resistivity have same temperature variation. Resistance and resistivity have the same temperature variation. So this was a short note that you should remember when we deal with different substances. So starting with the first substance, that is conductor. This is an important topic because your theoretical questions do come from here a lot. How does the temperature affect your conductor? If it can give you any name of a metal, like it will give you copper. What is the effect of temperature on copper if the temperature is increased? So you will directly say resistance of copper gets increased. Reason? Because copper is a metal. Metals are conductors. In this manner. In this manner, you have to answer. So firstly, if the temperature increases, then what happens? Relaxation time actually gets decreased. And if the relaxation time gets decreased, if you see the formula, both the formulas that we have, relaxation time is inversely proportional to both of them. So resistivity, this will also, resistivity or resistance, both of them will increase. Now the question comes is that resistivity and resistance is inversely proportional to relaxation time. It is inversely proportional to E, means electronic charge, but it is also proportional to N also, no, number density. So why am I not considering the number density? And if temperature increases, then number density increases. So according to that, density, this resistivity should decrease, but resistivity and resistances, both of these are still increasing. Electronic charge, so you all know that electronic charge is fixed, 1.6 into 10 to the power minus 19, that is fixed. Tau we have discussed. By N, what happens is that when we increase the temperature, it does not affect your number density, means number density, it remains constant. So that's why all the variations are done with respect to relaxation time now, and relaxation time is inversely proportional to temperature. So temperature increases, tau decreases, resistivity and rho increases. So I'll write down it also. On increasing temperature, R and rho increases. Also, apart from this conclusion, you have to remember the graph. In your board exams also, this graph comes. And in your entrances, this definitely comes. This is resistance or resistivity graph with temperature. Let's take the temperature in degree. No, let's take it in Kelvin only because it's the SI unit. And resistance and resistivity in their own SI unit, ohm and ohm meter. So the graph is in this manner. This manner it increases. At a temperature of 273 Kelvin. 273 Kelvin is basically 0 degrees Celsius. So the variation is very minimum. You can see till here. Variation is minimum. Variation is minimum with this. But after this, after 0 degree Celsius or 273 Kelvin, you can see it is beyond 0 degree, it's linear. It's kind of linear. This is non-linear. It was minimum and non-linear. After 0 degree, it's somewhat linear. Beyond 0 degree Celsius, it's linear. Do one thing, note down it for conductors, and for different materials, alloys and all, we'll discuss. Alloys, it's easy. Alloys is easy. This topic is easy. It's just that you have to remember in which case, which factor will dominate. N will dominate or tau will dominate. Okay, Maimuna, just inform me. Before leaving, just inform me once you can. Now, if you have alloys, then the variation with the resistance and resistivity is same, means it increases. It's just that in case of alloy, the resistance and resistivity increases with temperature, but the variation is very small. It means if I plot the graph, this is resistance and resistivity on the y-axis, and on the x-axis, if I take temperature in Kelvin, then I'll get the graph in this manner. Very slight variation. You can see, had it not been changing with temperature, it would have been constant in this manner. You can see slightly it has been inclined. So this shows what? This shows that resistance and resistivity, both of them increase with temperature. but the variation is small. Variation is small means very slight changes observed, not a significant change. Now, few quantities, just remember it. If you have insulators, if you have semiconductors, see, you have a chapter semiconductors in your second term, basically the last chapter of your class 12. So these questions no come from that portion, because that has the logics and the mechanism for semiconductors, for conductors, for insulators, for alloys, for conductors. So here you just remember the solution, because this is not necessary from current electricity. I'm just brushing you up. Otherwise, why and how, the whole reason, that will be dealt in semiconductors. So if you have conductors, temperature increases, resistance increases. Means resistivity, both of them increases. If you have alloys with you, temperature increases, resistance increases. If you have semiconductors, with you, or you have insulators with you, then temperature, if you increase, resistance and resistivity will decrease. Resistance and resistivity will decrease. One more thing that you have is known as superconductors. Semiconductors, you have conductor first, then you have semiconductor, and then you have superconductors. So for superconductor also, remember the graph of it. This is superconductors. Fourth, this with semiconductors and insulators are the third one, and this is the superconductors. Superconductors. So, what are superconductors? What is the mechanism of superconductor? For that, you have to understand the structure of conductors, structure of semiconductors. So, for that, you have a full chapter. There, we'll deal with it. Right now, you should at least remember the solutions of it. So this is resistance versus resistivity on y-axis. This is temperature in Kelvin. And this is the graph in this manner. This is the variation of graph. Actually, what happens in case of superconductors, at a certain temperature, which is known as the critical temperature, at a value of critical temperature, the resistance keep on changing, and then both of them changes exponentially, resistance and temperature. So these devices we'll be learning in semiconductors. Right now you will be only dealing with change in variation of resistance with temperature, that we'll see. All right, so first note it down.
Ma'am, could you explain superconductors again? Graph.
Superconductors, see, superconductor structure, that will take a lot of time. So I'm not explaining the structure, but just remember, in case of superconductors, what happened? See, this, let's say this is some temperature. Let's take it as 300 Kelvin, for example. Let's take it. And see, at 300 Kelvin, it will be having certain value of resistance. Then again at 300 Kelvin, it is having value of some other resistance. Let's say this is 1, this is 2. Then at 300, it is having again value 3. So what can you see? Resistance is increasing, but the temperature is remaining the same. So initially, the temperature remains the same till the critical temperature. We call this as a critical temperature. Then once it crosses the critical temperature, once you increase the temperature more and it is more than the critical temperature, then the resistance and temperature varies exponentially in this manner. Clear?
Yes, ma'am.
Now the variation of resistance with temperature. If you increase or decrease the temperature, you have seen how resistance varies for different materials, for conductors, for alloys, for semiconductors, for superconductors, for insulators. But how will you calculate the resistance? If you have different values of temperature, how will you calculate the value of resistance? So you have a formula for it. Resistance at a temperature, this is given by resistance at room temperature multiplied by 1 plus alpha. Alpha is coefficient of resistivity, a coefficient of resistance. Alpha getting multiplied by the temperature difference. Temperature that is there by the temperature of the room. I am repeating every term. RT is resistance at a temperature T, and this T temperature, this is greater than your room temperature. Then T naught is the room temperature. Whatever room temperature, it is usually 0 degrees Celsius. It is given, but it can give you anything. This is the room temperature. So this will be given to you. Room temperature will be given to you. Then RT is the resistance at a temperature. R naught is the resistance as room temperature. Resistance at room temperature. Room temperature or some reference temperature that we have taken it as T naught. This is some reference temperature. Then this alpha. Alpha is called as coefficient of resistance. This is called as the coefficient of resistance. And its SI unit is Kelvin inverse. This is the coefficient of resistance. So this is your final formula. T is what? T is the temperature. T is a different temperature that is given. So temperature T, you have RT. For temperature T naught means the room temperature, you have R naught as the resistance. So this is the direct formula which you have to remember. This, if you remember, you must have seen this kind of equation when you were in 11th. In 11th, you have done linear expansion, thermal expansion, volume expansion. It's similar to that only. So I'll give you a question, then practice that. I'll give you a numerical on it. So all of you try that question, first note it down, try that question and submit your answers based on this formula only. See, this question looks lengthy, but if you look at it, you have room temperature. Room temperature means RT. Then you have resistance also. So you have resistance RT and you have T also, T naught over here. T naught and R naught, both are given. Then what do you have? You have voltage and current. So voltage and current can give you resistance. So you have both the resistance, you have the temperature, you have to find out the other temperature from it. Alpha I'll give you. Yes, alpha I'll give you. Alpha I'll give. It will be 1.7 into 10 to the power minus 4 degrees Celsius inverse. All right, by now at least you must have tried and understood the question. Did anyone get the answer?
1 month. 1 month.
Okay, last minute, last minute. Take the last minute. Rest of you also wind up your answers. Which value? Which value? Just say, Shravya, which value you're getting? In degree Celsius? Write down the value. It's okay. It's okay. Write down the value. I'll see. Let's discuss it then. See, it says what? It's saying it's still less. It's not huge. This is still less than the original answer. You're near to it. It's around 841 something. So you are still having the lesser answer, Shravya. 791. It's 847 or 840 something. 840 something. I'll see the answer. So what does it say? It says an electric toaster uses nichrome wire for the heating element. It says that the resistance at room temperature means the room temperature is 27 degrees Celsius. All right. Resistance at room temperature that we take R naught. This is what? 75.3 ohm. The other temperature, what is the steady temperature? We don't know. But we know the voltage is 230 volts and the current is 2.68 amperes. So from here we can get the value of R. R is what? V is equal to IR. So R will be V divided by I. From here you can have the value of resistance. So first let's have the value of resistance. And also you have the value of alpha. So only Shravya tried this question. What about others? Did you at least try it?
Yes, ma'am.
Okay, okay. Then it will be easier for you when we are discussing it. Alpha is also given 1.7 into 10 to the power minus 4 per degree Celsius. Now let's calculate resistance first. Resistance will be, this will be RT. This will be 230 divided by 2.68, which is 85.8 ohms. So this is the resistance. Now you have the equation with you. What did we study? RT is equal to R naught 1 plus alpha delta T. Delta T means T minus T naught. Basically T minus T naught. So let's put in all the values. R is coming what? RT is coming 844, Sarah. Okay, okay, good, good. Yes, yes. It is near something to it. I'll check it. I'll check the answer. RT is what? RT is 85.5. This is RT. This much ohms. This is your 85.8. 85.8. This is your resistance value. This will be 85.82 ohms. R naught is what? 75.3. 1 plus alpha is 1.7 into 10 to the power minus 4. Delta T means T minus initial temperature. Initial temperature is 27 degrees Celsius. So this is a single equation which you have to solve. So let me just check its answer.
Ma'am, don't we have to convert it? The
No need to
27 degrees?
convert it. See, the reason that you don't need to convert it is that when you take the change in temperature, convert 27 degrees Celsius into Kelvin, then convert T also into the Kelvin. The difference that you will get, no, that will be same if it is in Celsius or temperature on degree Celsius. That's why we do not convert it. Apart from this, you can also see that alpha is given in per degree Celsius, not Kelvin inverse. So since it is not given in Kelvin inverse, that's why we are considering it in degree Celsius. Then only we are able to solve it. Had it given in Kelvin, then also temperature difference you need not convert. See, why temperature difference you don't need to convert. For example, if it's, let's say, 27 degrees Celsius and it's 25 degrees Celsius. 27 degrees Celsius, if you add 273, this becomes 300 Kelvin. And here, if you add 273, this becomes 298. It becomes 298 Kelvin. Subtract both of them. This is coming 2 degrees Celsius. Subtract them. This is coming 2 Kelvin. Both of them are 2. That's why you don't need to convert whenever there is a temperature difference. If difference is there. Otherwise, for a different operations, you have to do. Okay, so you're getting 844 also, no? Okay. So temperature will be 844. I remember it was 847 or 844 around this degree Celsius. Others also, please cross check. Two students, Sarah and Shravya, they are getting 844. So it's around this only. All right, so note down. One more thing before you start noting it down. Remember, regarding few points regarding alpha. If you have a conductor with you, no, then this alpha's value is positive. If it is insulator or a semiconductor, then this value of alpha is negative. And if it is an alloy, then it will be positive, but alpha is very small. This is very small.
Ma'am, what is alpha for superconductors?
Yes. Alpha for
Superconductors.
superconductor, it's also negative. Superconductor, it's also negative. For alloys, it will be positive. It will be positive. It's just that it will be very small, means 0.0000 something. You can see it easily with the help of the powers of 10. It will be 10 to the power minus 31 or such huge numbers. All right, all right. Those who have to pray, you join us till the time we'll start with internal resistance. So written, rest of you. Okay, so internal resistance is small topic, so let's start with it. See, internal resistance, EMF, terminal potential differences, these are small topics, but they have a huge significance when they come together. They are not independent topics, means all of them are related on one another. This is different from the previous ones. If you are studying it from here also, you'll be able to understand. But the thing is that all these are interrelated: terminal potential difference, EMF, internal resistance, and this is also related to your chemistry. In chemistry also you have a topic. Now for understanding is, see, if you say a cell or a battery, actually the internal structure of a cell or a battery is in this manner. There's a container of it, and there are two electrodes in this manner. Two electrodes here, positive and negative. One anode, other one is cathode, that you have as the electrodes. In the structures of cell which is connected, and then these electrodes, these are dipped into an electrolytic solution. Electrolytic solution. So internal resistance, what is basically the resistance that is offered by these means the electrolytic solution, resistance offered by the electrodes and the electrolytic solution in a cell, that is known as internal resistance. See, resistors you have studied, those are external resistors which are connected in the circuit. Now there is an additional resistance that is offered by the cell. If you see, we always connect them to a cell, no? So apart from this external resistor, there is always an internal resistance offered by the cell. Now what happens, sometimes we neglect it if it is very small, if the internal resistance offered is very small. So internal resistance is basically this resistance that will be given by the electrodes and the electrolytic solution. Resistance can be anything can give you resistance. For example, if electrons are moving and the walls of the wire came, so now it will be giving it resistance. Electrons will not be able to move. Similarly, resistance can come from any medium. It can come from the electrolytic solution. It can come from the electrodes. So this becomes the internal resistance. In here, why we call it as the internal resistance? Because you are not fitting a resistor or a device in the circuit with the help of wire or something. Here what has happened, you are giving the resistance from the cell. The cell is itself generating the resistance within itself. That's why it is called internal resistance. So internal resistance, this is the resistance offered by. Two things you have to remember. One is what? One is the electrodes. One are the electrodes. First one is the electrodes. Second one is the electrolytic solution. Both of these offer resistance, which is known as the internal resistance. So offered by electrodes and electrolytic solution of the cell. So there are various factors on which then this internal resistance depends. In chemistry, you will study it, but in physics also the question can come. It depends on the nature of electrolytic solution. It depends on the separation between the electrodes, the kinds of electrodes that are used. So try to find out what are the factors that affect the internal resistance, because internal resistance gets affected by certain factors. Now, apart from this, what did I tell you? EMF, electromotive force. EMF's full form is electromotive force, but this is not a force. Forces that are there in nature, for example, electrostatic force, which we had studied, or which you must have studied in 11th, gravitational force, all these forces, those are actual forces of nature, which are given as mass into acceleration. This is not a force. It's just a name has been given by convention and we are using it. Electromotive force. But do not equate it to force and do not use the properties of force. Whatever properties of forces you have studied, don't apply it over here. This is completely different. This is electromotive force. Electromotive force means EMF. Now this is related to the potential difference or the voltage. This is same as potential difference with a slight difference. Only a slight difference is there. It's just that in an open circuit, the maximum potential difference that is offered by the cell. Rest of the phenomena, properties of voltage is similar to electromotive force. Firstly, don't confuse it with the name. It's a misleading name. It's a misnomer. Electromotive force, it's not a kind of force. It's a voltage. It's potential difference. The SI unit is also voltage. Same everything, all the properties of voltage, all the phenomena that are associated with voltage, everything is same. Sometimes V is replaced by EMF. Many a time if internal resistance is 0, then your EMF is directly equal to the potential difference. That we'll see how. Through calculation, that is in your syllabus, you will see. But electromotive force is what? This is basically the maximum potential difference. I'll write it down. It is the maximum potential difference across the terminals of a cell in an open circuit. Open circuit basically means off circuit, when the current is not flowing, off circuit usually. Off circuit. Then the potential difference whose value is maximum, you call it EMF. So SI unit will also be volt. All the properties of voltage are valid. Now see, if this is connected in this manner, no, this is a representation of cell. Cell is given in this manner only. Now, in the representation of cell, you must have noticed that I always draw a bigger line and a smaller line together. This negative line, this smaller line shows negative terminal. Negative terminal means the potential here is lower. And the positive, bigger terminal, this shows that potential over here is higher. This is how you must have seen the circuit I draw in this manner, a bigger line and a smaller line. It can be in this manner also, smaller in this, or but the bigger line has to be the higher voltage and this has to be the lower voltage. Now, how is the EMF given? EMF is represented through this capital E only. This is given by VH minus VL, means higher potential minus the lower potential. This is what is how EMF is given. For example, VH is, let's say, the first positive terminal is 10 volts and the shorter terminal, this is 2 volts. Then your EMF of the cell becomes 8 volt. So this is not exactly the same as voltage. As you can see, voltages are different. The difference you are getting is EMF. One is potential at lower, potential at higher. Their difference, you call it as potential difference, and that is which is having the maximum value in an open circuit. You call it as EMF. So a few points regarding it. Potential terminal potential difference is what? If this is EMF is the maximum potential difference across any circuit, then what do we call as the terminal potential difference? Terminal potential difference. Now see, carefully see, all these three are just confuse you by their name. Properties are similar. Terminal potential difference. This is the maximum potential difference that is applied across and everything remains the same in a closed circuit. This is just the difference. This is what we call as a terminal potential difference. That's why I'm saying all these terms, EMF, voltage, potential, terminal potential, you will see all of them have the units continuously, V. Sometimes terminal potential is written, sometimes E is written instead of the cell. Instead of writing capital V, sometimes E is written. Sometimes terminal potential difference is written. So there's a slight difference in each of them. Majorly, they are having the same properties. They are voltage only, all the properties of voltages. But if you look at precisely, EMF is basically for an open circuit. Terminal potential difference. This is the potential difference across the terminals of the cell in a closed circuit. Your circuit has to be closed. Closed means a running circuit. On, the circuit's key is an on. Or you can even say potential difference across the external resistor that is connected. You can even say it's the potential difference across the external resistor. External resistor which is connected in your circuit. See, let me give you an example. What is an external resistor? What is an internal resistor? See, I have given you here, you have a resistor and this is connected to a cell and the internal resistance of the cell is connected along with it. It's actually not connected, but in the circuit, how will you show? You cannot draw a cell and show the internal resistance of it. So just attach a small resistor adjacent to the cell. That will show you that it's the internal resistor. And usually in most of your books also, in your NCERT also, external resistor is maximum time represented through capital R and internal resistor is represented through small r. This helps us to identify that this is the internal resistance, meaning a resistance offered by the cell. And this shows us that this is the external resistor, means the resistor that is connected along with the wire. The whole setup is made. Did you people have your practicals of this rheostat and all, the wire, ammeter? Your practicals are still left. You had, Khalid?
Yes.
And let's say it is connected, this key is connected. Okay, so you people have had your practicals. Good. And this key is connected and this is the wiring is done. Let's say this is 9 volt. So this is what? 9 volt. This is the external resistor, and this is the internal resistor. This is the internal resistor. Let's say this is let's take the value as 10 volts. Not volts, ohm. I have also written volt here, ohm. By volt, it will be 9 ohm. Let's say this is 10 ohm. There will be a potential difference across this. And let's also write the voltage of the circuit. Let's say this is 12 volts. This is the key. Now understand in this circuit what all things you have. The potential difference across this. There will be a potential difference across this. That you will call as the terminal potential difference. Why? Because when the circuit will be open, when the circuit will be closed means when the circuit will be on, the key will be connected, charges will be flowing, current will be running. Then there will be voltage across this resistor that is connected with the help of wire, the external resistor. That potential difference you call as the terminal potential difference. Now, here again there will be a potential difference. Internal resistor will be also having a potential difference when the circuit is not working, means not working as in the open circuit is there. You open the key, that key tap that is has been placed in this manner, open the key in this manner. No charge is flowing, no current is flowing. So no current will go through the external one, but current will be still not current. Potential difference will be still there. Why? Because you have a cell. Electrodes are there, electrolytes are there, and electrodes and electrolytes whole mechanism is, I think, there in your chemistry syllabus already. So if this is the potential now difference that is offered, this is EMF. So let me say this is 9 volt. So V is equal to 9 volt. This is the terminal potential difference. All right. If I say the voltage here is what? 12 volts, and let's say the voltage across this is 1 volt. Then calculate the potential difference. 12 minus 1, that will give you 1, because you have to consider it for the entire cell. The cell has voltage 12 volt, and internal resistor has voltage 1 volt. So how do we calculate the EMF? EMF is always potential difference, so you have to subtract it. So 11 volt, this will be the EMF. EMF means electromotive force. This is how you use it. So you have questions on it, but before that you need a little theory portion. But I think you should write down all these points first. Then I'll teach you that theory portion and the formulas for it. Then we'll do a question. Because first now understand the differences between them, understand what is internal resistance and what is the difference between internal resistance and an external resistor. This is usually, most of the time actually, represented through small r. An external resistor through a capital R. Yes, maximum time it will exist. Actually, it exists most of the time. It's just that the value is sometimes so small that we can neglect it. And when to neglect and when to not neglect, that will be given in the question. Okay, Maimuna. Yes, Maimuna. Now we'll be doing after this the questions on it and then the combination of resistances. So you can. Now the theory portion that I was telling you regarding the formula, that is very important. This was the basic, to understand the basic. See, if you are given a circuit, let's say this is external resistor given. Now, if different resistors are there, because there cannot be only a single external resistor in your circuit, if there can be, yes. So external resistors can be given in different manners, in different arrangements. So what you have to do, combination of resistors, that we'll do in the next class. The way we have done combinations of capacitors in series or parallel. Ultimately, what you get in capacitors also, what we did see, we had seen no, that we have finally equivalent capacitance. Similarly, in external resistors also, you will have equivalent resistor. So ultimately you will get that single resistor which I was drawing. So you have wire connection, you have connected it with a resistor. It can be a single external resistor, it can be combination of resistors can be connected in series, resistors can be connected in parallel. This can be the arrangement. Now how to solve it, that you know, you can reduce it, that we'll do again also, but you also know it, that how to solve it. So ultimately you'll get this equivalent resistor, equivalent resistance. Now we have connected it to a battery. The battery is having its internal resistor. So this is smaller, and this is EMF of the battery, of the cell. Now let me say current I is flowing through it. Current I is flowing through the circuit. Now, Hania, what was Ohm's law? Not the whole statement, just the formula of it. Ohm's law. Question is, what was Ohm's law? Shravya, the question that I asked. Yes, Hania. Yes, Hania, I'm calling you.
V is equal to IR.
V is equal to IR. Exactly. Shravya, which question? Right now.
I thought you were calling me.
Okay, no, I was asking Hania. So good, Hania. This is V is equal to IR. So if V is equal to IR, then I is what? I will be equal to potential difference by the resistance. So from this circuit, now look at this circuit. This is a typical circuit that you get. Current will be what? Potential difference in this circuit is what? This is basically EMF of the cell divided by EMF of the circuit. Now resistance, there is not a single resistor present, there are two resistors connected. So total resistance will be what? Capital R plus small r. This is the formula of current. Firstly this, then V is equal to IR. Now we know I, we already know R. So V, how can you get? V will simply be, put the value of I is E divided by R plus R. This is I multiplied by R. So this is another formula of potential that you get. This is what? This is the terminal potential difference. Terminal potential difference across the external resistor, capital R, that you have to calculate. Now, terminal potential difference, apart from this, for the calculation, terminal potential difference, this is actually given by EMF. It's the potential difference, so we have to take the difference also. So this is given by what? This is, let me write it in words, that will become easier. It is given by EMF minus the potential difference across internal resistor. See, this is what am I writing? there is a potential difference across the internal resistor, and there is a whole EMF of the cell. This difference between both of them, that will give me the terminal potential difference. So terminal potential, another formula for it. This is also valid. If it is coming, then you can use it. But maximum time, this formula gets used. So EMF of the cell minus potential difference across the internal resistor. Current I is flowing, resistance is R. This is a very, very, very important formula. B is equal to E minus IR. So note down these points and I'll give you a question and try that question based on this. Many a times the potential difference across the internal resistor is not given. So in that case, what will you do? In that case, if you know the current and you know the internal resistance, then do this IR. See, this is what? Potential difference across the internal resistor. So I multiplied by small r gives you potential difference across internal resistor. If it is not given, because most of the times value of small r is given and you know the current, so you can easily calculate. Check the unit. Shravya, answer is correct. Magnitude is correct. What is the SI unit that you have written? Yes, yes, now it's correct. Others also, by now, first part must have been completed. Submit your answers. Yes, yes, Sarah. Good, good, Sarah. Yes, second part is also good. Correct, Shravya? What about others? Where are these? Khalid, Salman, your answers. Samaira, Hania. This is an easy question, no? Yes, Khalid. Good. Salman, Samaira, Hania, you also try this question? Yes, Samaira. Good, good. Samaira has also answered. Okay, okay, good, good. So first part, all of you have answered. Hania, just check your calculations once again. I think there's a typing error or what? Just check it once again. How, Hania, you got that answer? That is the EMF of the cell. Current, electric current you have to find out. Whose formula was E divided by R plus R. See, first part, let's discuss then. Current is given how? Current is given in this manner. Current is EMF divided by sum of all the resistance. Whether it was R1, R2 or any resistor given, sum of all the resistance gives you. EMF is what? 22. This is 10 and this is 1. So you get what? 22 divided by 11, which is 2 ampere. Anya, is this clear? Did you see wherever you were committing errors?
Yes, ma'am.
All of you try the second part also, second, third part. These for the, yes, third one correct. Good, Shravya. So Shravya has almost solved the question. Just try the fourth part also. What about others? Why it is taking you people time? It's not a lengthy question. Simple, easy multiplications are there. Yes, Khalid. The way you have done the second part, no, answer the third part also. That is easy. Yes, yes, good, good. Khalid has also reached the last part. What about you, Sarah? Now you stopped answering. You had answered the first part. Yes, you have answered the first part correctly. Sarah, try the second and third part also. Okay, last 2 minutes. Please try to solve this question. It's not a tough question. And then we'll discuss it after 2 minutes. Last 2 minutes. Yes, Shravya. All parts are correct. Good, Shravya. All the 4 parts are correct. Yes, Sarah, correct. Second part's answer is right. Fourth, slight error, Khalid. Check once again your calculations. Fourth part, Khalid, just recheck it. Good, Salman. Just try the last part also. Yes, Sarah. Third part is also right. So you people are on the last portion of this. So Myra, where have you gone? Trying the question? Yes, now it's correct. Now it's correct. Khalid and Sarah, both of you have done it. Now I think it was ample time was given for such a small question. Now let's discuss it. First part, we have already discussed it. Second part, potential difference across the external resistor. Current, you know, potential difference is given by how? Just use your Ohm's law. I multiplied by capital R. Current is 2, resistor is 10. This gives 20 volt. That's how we'll get it. Third part, potential across difference across this resistor. This is capital I multiplied by small r means resistance across this. Current is 2. This is 1. This is 2 volt only. Now the fourth part. Fourth part is what? Terminal potential difference. See, terminal potential difference will be what? Use this formula. R plus R means I is already there and multiplied with capital R. Or no, better way we use that formula. Answer for Salman? Fourth part? No.
Yeah.
No. Very, very less. Just try again. Use simply E minus IR. So EMF is what? EMF is 22 minus IR is 2. Or let's write 2 into 1 again. So that makes it what? That makes it 22 minus 2. That is 20 volt. Or even if we do it with the formula that we had started with, R plus R multiplied by R. See, R E divided by R plus R. E is 22, capital R is 10, small r is 1, multiplied by capital R is 10. This is 22 divided by 11 multiplied by 10. That is 2 multiplied by 10, which is giving you 20 volts. So in both the cases, you are getting the same answer. So note down this. All those who have not. Anya, is this clear? Any doubts in this?
No, ma'am. It's clear.
Okay, good. Done? And what about others? Still doing? So most of you have completed it. All right. I was looking at your assignments which you had submitted. Salman, you had submitted it on the WhatsApp or not after that correction? Or did you upload it on the website or what?
I sent it on the WhatsApp, but before that, I already uploaded this one, direct answer one, on the website.
The solution one, have you given it on the WhatsApp? I asked you to submit
Yeah,
it, to rewrite
I
it.
sent it to Learnivio.
Learnivio, you have submitted.
Yeah.
Okay. I didn't receive Salman's corrected one. I have only the marked one, the answer one. Okay, Salman, I'll see. I thought you have only uploaded it on the site. Zaid is absent today. Khalid's answer was correct. We can discuss it from Khalid's paper directly. So he has done all the questions, but let's discuss it from the third one. See, you people, current was given to you, charge was asked. You were not given the value of the charge. What we do, we know the value of charge equation with us, then we calculate current by either differentiating with it or taking the average of it up as per the question. Here current was given to you. So if current is given to you, what will you do? You have to find out charge. From here, charge will be current multiplied by dt. Now I have to find out the whole one. I have to expand it. So this will be what? I have to integrate it. Integrate current from when to when. I am integrating with respect to time. So whatever time was given in the first question, Khalid must have written 3 to 5 seconds was the interval. So it will be 3 to 5 seconds. And then whatever is the equation of current given. In this question, it was given 2t cube plus minus 3t plus 1. He writes so small, Khalid.
It's minus.
Minus 3t, no? But you have done all the questions well. Good. You have done it. All the questions well. Salman, I didn't see yours because I didn't receive it on the WhatsApp. I'll check it again because I got to know that second one you have uploaded it on the website only. So that's why I didn't receive it. All right, I'll check it. Others I've seen. Others. Yes. Others I've seen. Shavya, you didn't do it because your first class was missed. So see, this is the value of current that you have. Now you just put it and then integrate it. In this manner you have to do. If current is value is given, similar that was given in the fourth question. You were given value of current. Current was 4 plus 2t. You have to find out charge. Charge will be multiplication of I dt. Now you have to expand it. You want to find out the whole charge. How will you get it? You will get it by integrating it. So if you are given current or if you are given charge, you have to first look it. And in fifth part, everyone has done it well only. High potential to low potential. This you have to remember, high potential to low potential. All these questions were from your previous years only. So Sarah has also not done, no? Sarah, you didn't do the assignment, no, in the last class? Memuna was absent. Samaira have received. Yes, so fifth part was correct. Now, Samaira, did you understand? If charge is given, don't do it in this manner. This was valid. Sarah, you had sent it. Okay, Sarah. Good, Shravya. If you can do that, then it will be helpful to you. Okay, Sarah, I'll check. Sarah has submitted, I'll check. Then Samaira, in this manner only. If you are given value of charge, then simply you can find it out by differentiating it. But if you know charge, if you want to find out charge, then you have to integrate it from T1 to T2, whatever is the value. Then Hania, similar case. Hania, same thing. So now understood, Hania and Samira? Mana received.
Yes, ma'am.
Okay, so clear to all of you the assignment of the previous class. Whenever current is given, differentiate it. If whenever charge is given, differentiate it. Or if you have to find out the interval, then calculate the interval by putting the method that we have done in class. What you have done is that you have put in the value of intervals in between. You are not getting the change in current. You want to find out the change in charge. That's why we use that. In this case, current's value was given. So simply integrated from wherever the time difference was given, time interval is given. All right. So now the next topic that is left, this completes a terminal potential difference portion. Now the next topic that is left is your combination of resistors. But for that, I want you all to at least revise the combinations of capacitors, then it will be easy, because whatever you have done in capacitor, it's just the same. Instead of a capacitor, you have a resistor connected. All right, so okay, take care. Let's meet in the